Good morning, everybody, and welcome to day 2 of Advancing Sciences. My name is Andrew Sen. I'm the Vice President of Strategy and Marketing at Integer Holdings. Integer is a contract developer and manufacturer of medical devices. We have about 2,000 people in the Twin Cities and 8,000 employees worldwide, all working on the development of manufacturing of medical devices. I'm involved in Advancing Sciences because I think I get excited about STEAM careers. I think they're very exciting careers. They're doing great things in the world. Also, a lot of STEAM careers have the opportunity for people to make the world a better place, which is why I'm involved in this program. Yesterday, you learned about the American Heart Association mission to be a relentless force for the world to live a longer, healthier lives. Plus, you had the chance to learn more about STEAM and the impact on heart disease with Boston Scientific. Today, we'll dive into process capability with Amatec and set you up with local leaders for our first day of speed mentoring. As time allows, we'll wrap up today's program with a brief Q&A. So let's get started. I'll turn it over to Chris.
Thanks, Andrew, and welcome, students. Today, we have the Amatec team with you. My name is Chris Brooks. I'm the General Manager for our Engineered Medical Components business. Amatec is a leading global manufacturer of electronic instruments and electromechanical devices. One of the 14 divisions is the division that I work in, and we get the opportunity to serve the medical devices market. And so today we have a team that's going to be bringing to you an engineering term called process capability. We've got David, Krishna, Sean, and Eric, and they're going to guide us through that. And just a little background, these guys are all engineers, and they have a real passion for the sciences. I'm an engineer as well by undergraduate degree. And I really love the technical arena as well. And I think it's one of the best paths to success in any career that young people would choose. So at this point, I'd like for David, Krishna, Eric, and Sean to just show themselves and say hello to everyone.
Hi,
let's get. Okay, so after everyone has said hello, I will turn it over to David, and he will take us through today's lesson. So thank you, guys.
Okay, so today, guys, we're going to show you a little bit about process capability analysis. We're going to give you for the everyday problems that we as engineers encounter and essentially show you kind of one of the ways we go about solving problems.
What is capability analysis? To understand the use of statistics in engineering, let's review a few basic statistic concepts. Mean. The mean is the average or geometric center where data tends to. Standard deviation. The standard deviation is a measure that is used to quantify the amount of variation or dispersion of a set of data values. It is denoted by the Greek alphabet sigma. Histogram. A histogram, as seen in the picture with the blue bars, is an approximate representation of the distribution of numerical data based on its frequency of occurrence. Normal distribution. The normal distribution is a bell-shaped frequency distribution curve, which helps describe all possible values a random variable can take within a given range, with most of the distribution area in the middle, next to the mean. This is shown in the green and yellow areas. A few in the tails, the red area at the extremes. Specification limits versus control limits. Specification limits are values between which products or services should operate. For example, you print labels for a shipping process. If the labels are too big or too small, they will not feed into your printers properly. Control limits are used to detect signals in process data that indicate a process is not in control and therefore not operating predictably at plus or minus 3 standard deviations from the plotted statistical mean. The Process Capability Index is the ability of a process to produce output within the specification limits. The red dashed lines in the picture show the upper specification limit, or USL, and the lower specification limit, LSL. Process capability indices measure how much natural variation a process experiences relative to its specification limits. The narrower the yellow area under the curve, the higher the process capability index, or PPK value. A PPK value above 1.33 is considered a very capable process. This is an example of a cardiac mapping catheter. These catheters are used in the heart to read the ECG signals of the heart and create an anatomically representative image, showing where an arrhythmia may be present. Electrode locations are critical as the system uses the electrodes to accurately represent cardiac maps created and interpreted by the electrophysiologist. Our engineers are seeing that the electrode positions on the spine assembly are drifting out of specification on the high side. This is a high-level process flow of the spline assembly. We start by welding the electrodes. This is accomplished by welding a very fine wire to a small diameter platinum ring. The completed product is called the electrode assembly. We then laser drill holes into cut-to-length rubber tubing in very precise locations. Lastly, we combine the welded electrode assembly and the drilled tube by stringing the wire through the hole, much like threading a sewing needle. We pull the wire all the way down until the electrode bottoms out on the hole. Tolerance stack-up for assembly of the ECG sensing electrodes is causing parts to go out of specification. First, let's review the specifications that would influence this. We will review the electrode ring assembly, laser drilled tube, and spline tube assembly specifications. Ring weld. Let's look at our ring welding specification. Notice first the dimension from the edge of the ring to the weld location. This dimension controls where the electrode will contact the hole. This dimension is 0.25 plus or minus 0.15 millimeters, so it can move a total range of 0.15 millimeters left or right. Let's then look at the ring. The tolerance isn't on here, but the standard rings are 1 millimeter plus or minus a tenth of a millimeter. The addition of these two tolerances equals 0.25 millimeters. Based on all of this, the dimension from the edge of the ring we are measuring to the weld location is 0.75 millimeters plus or minus 0.25 millimeters. Drilled spine. We now go to our laser drilled spine specification. Here you note dim A and dim B. Dim A is where our first electrode is placed. When we drill these tubes, it's where the first hole is placed and all other positions reference off of this hole. So it will be disregarded in the stack up. Dim B, however, is important to where each electrode is placed. The tolerance here is 0.15 millimeters, and we multiply it by 7 because we have 7 electrode locations affected by this dimension. Total stack up here is 1.05 millimeters. Spine assembly. Finally, we look at the spine assembly specification. First, from the work we just did, we know that we have plus or minus 0.25 millimeters tolerance for the welded assembly and plus or minus 0.15 millimeters tolerance for the drilled tube. Adding these together equals plus or minus 0.4 millimeters of tolerance. We multiply the 0.4 millimeters times 7 because there are 7 electrode locations affected. This provides 2.8 millimeters of variation. Now we look at the electrode location tolerance stack. Here we have plus or minus 0.5 millimeters of tolerance, again multiplied by 7 to get 3.5 millimeters variation. We add up all of this variation and we get a total of plus or minus 6.3 millimeters. Variation adds up, and therefore design for manufacturability is key. This is all important because to get the electrode locations within specification, we need to implement controls within this process. Now we'll look at the data from the assembly process. I'll begin by breaking down the data for the first ring. You can see this chart looks good. The histogram is centered and there is clearance in the upper and lower specification limits. We observe the p-value is above 0.05, indicating a normal data set. The ppk is 1.67, which is greater than 1.33 and therefore showing a strong capability. The pp is 1.68. The closer the ppk is to the pp, the more centered your process is. I am now going to run through the charts for electrodes 2 through 7. I'll run through this data a little quicker than before. As I go through them, I want you to pay close attention to the histograms. The process is looking pretty good on ring 2, ring 3, ring 4, ring 5. But wait, what is happening on ring 6 and ring 7? Why are they starting to shift? Ring 8 we see has finally gone out of specification. The distribution has clearly shifted outside the spec limit. Our ppk is awful at 0.028. Remember, 1.33 is considered good. Our pp, on the other hand, is 1.62. This shows there is room for improvement. Our distribution is tight enough that we can do a process shift, but first we need to figure out what is causing the problem.
Sean, you're currently on mute.
So we walked you guys through what the problem is, and now we're going to walk you through on how to solve the problem. So let's look at what we call a fishbone or a cause-effect diagram, and to see where the problem lies. So you can see the different categories on this diagram. There's man, method, measure, machine, material. These are the 5 buckets that we can look to try and solve what the problem is. Sometimes it's as simple as there's a single problem, and sometimes it's more complicated than that. There's multiple factors that could contribute. So let's look at this and think about what could the assembler do to cause the pattern to go out of spec? What could be happening in the process to cause this? What could the machines be doing to cause this? What could the material do to factor this? What could the measurement system do to be giving this result? So when we look at the assembler, the position is changing at a consistently increasing rate, but the assembler is well trained in the technique. So it's highly unlikely, due to the nature of how the stack up occurs, that the assembler is the root cause. The process of placing the electrode has some influence, but we're using a contact point in the weld as our stop point for where the electrode terminates to. The machine could be causing it with the laser drill pattern that you saw in the process flow. Maybe our laser drill hole pattern is off, but we look at the data and we know that the pattern itself is not off. But what about the material? Well, you guys don't get the luxury of feeling these spines, but the material is it's a soft rubber tube material with metallic electrodes on it. When you feel it, you can feel that it can stretch, it can be easily manipulated, and we notice that the change is coming after the parts are swaged. So it's likely that the stretching is the root cause to look at. So then we have to ask ourselves, well, what can we do about the stretching? So we'll eliminate it and we'll select stretching as the root cause. So when we look at it, we look at the laser drilled spine print, and these are the holes that are drilled where the electrode terminates to. And we say, okay, well, what can we do with this? Well, if the tube is stretching and it's stretching in a way that's predictable for what the data was suggesting, we can compensate this pattern. So we can adjust the hole locations to determine or to compensate for the stretching that occurs in the process. So we select these new dimensions. We modify our laser drilling program to produce the holes in these dimensions. So now we went through our process again. We made new parts, we made new spines, and we measured them to see what the effect was. So again, when you look at the ring 1, you see a very similar distribution to what you had seen before. We didn't really change the location of ring 1. But now we've started to compensate the pattern. And so when you start to look at ring 2, 3, 4, you see that the distributions on all of these now are much more centered than they were before. The P and the PPK all are very acceptable values. And we look at ring 8 finally, and now remember ring 8 was the one that had went out of specification before. When we look at that, you can see now it's nice and centered. It's very much in spec. It has a PPK above 1.33. Here's a snapshot of what we were looking at before with ring 8. So now you can see the before and after, and you see that it's moved to be more centered within the upper and lower specification limits. Okay, so we will turn it to the group now for questions.
So there was a few questions that came up in chat. Excuse me. First one, Sean, would be how long does a process like this take your team?
So to develop and troubleshoot for just the cycle that you've seen there, that might take 3 to 5 days to get through, do, and build more parts and analyze. To develop a full process usually takes 3 to 4 weeks just because you need to observe, measure, analyze, and then make your best estimate on how to fix the problem, and then measure and analyze again.
Sounds good. And a second question would be, what types of degrees do the staff working on the spine assemblies have?
So the individuals that are making the product just have they're what we call assemblers, operators. They have not college degrees, they have high school degrees. And then we have technicians who help kind of are the first line of troubleshooting on our product lines. And they have 2-year degrees, vocational degrees in either engineering technology, robotics, or even in automation. Then the engineers that work on our products, we have from all disciplines: mechanical engineering, electrical engineering, industrial engineering, and they're working out the process, working out the data, they're in the role of the process engineer, the product development engineer, or the quality engineer.
And then another quick question: what other types of what other types of projects do the teams work on?
So we develop processes for many medical device industry technologies. We do anything from make a very simple singulated wire at a very high tolerance. So most of the wires that we deal with are the size of the human hair or even smaller. That's kind of what our everyday is. And then we take that from some type of subassembly where we put one or two components together, or we do value add like you saw in the catheter that is there, where we build a catheter assembly and we give that to our customer. And we do that work for most of the major OEMs. And so they come to us with their designs, their problems, and we figure out how we can help it solve their problems with the technology that we have. Our core competency is laser processing, so most of the technology we have in our building is using lasers to do some sort of work.
And then what is the favorite part of the team's jobs?
My favorite part is helping see the solutions that we develop help other people. There are days that it can be very exhausting in this line of work, but it really hits home when you see how your product that you have a part on in all of these larger systems and stuff that a lot of the Abbott's, Medtronics, Boston Scientifics all develop, how it helps other people and the impact to people's lives that you make. Eric, Krishna, David, you guys want to comment on your favorite part?
So go ahead, Eric.
Okay. Mine's very aligned with what we talked about here. So being on the sustaining side, getting a problem delivered to you and working through the process steps to improve that problem. It's rewarding once you put the changes in place and you start to see the overall results and the impact it's had to the process and the metrics associated.
Yeah, so I think my favorite part or most rewarding part is every time I go into a hospital room or a clinic or something like that, I can normally point out something that the Amatech group has had a hand in. And just to see that it's positively impacting everyone's life is has been very good to see.
So hey, this is Krishna. So my favorite part is almost the same thing like David said, is if you go anywhere to the hospital or a clinic, or even if you know somebody within your family using some product that your company has worked on, it is a very good feeling that you take back home. But on a day-to-day basis, the most interesting thing about my job that I feel is when these problems occurs, the way we try to think and try to solve those things, it's almost like how do I put it? It goes on like an investigation, not as theatrical as a crime scene investigation that you find on the TV, but it's almost pretty much we try to identify where did things go wrong and how do we fix it, how could that happen. That's one kind of situations that we encounter on a day-to-day basis. And the other side of the thing that is very interesting is predicting what could go wrong. That's another key thing for an engineer like us. So these kind of activities makes my job very interesting.
All right, any other questions from the group? Anything else?
Okay, well, if there are no other questions, and I did not receive anything, Jackie, from text, so we can certainly handle some things as we move forward if we need to on the question side. But thank you so much to the Amatech team. It was really nice to see you guys talk about what you do on a daily basis and engaging in our session. And now let's jump into our speed mentoring segment.
Okay, thanks, Chris. Yeah, today we have more than 30 local leaders joining small groups of students to answer questions you might have about college, team careers, or any other topics you might want to discuss.
And in a minute, we'll split into breakout rooms where you'll have the opportunity to ask your questions. We encourage each of you to turn on your videos and use the chat box to ask questions and talk with the mentor in your group. After 10 minutes, you move to a new room with a new mentor. This segment will last for 20 minutes total, and you'll meet with 2 different mentors and several other students by the end.
And we've included some sample questions on page 10 and 11 in the student program, which is sponsored by Integer, to help get you started if you have any difficulty with questions. And with that, we'll send you into the first room. See you back here in about 20 minutes. Okay, welcome back, everybody. I really want to sincerely thank all the mentors for the time you spent today with the students. Hopefully the students found it insightful and enjoyed their time with the mentors. We'll be having another session later this week. With the remaining 9 minutes here, I wanted to ask if there were a few general questions that were asked via the chat space that Chris and I will be answering here. So just wanted to read a few of those off, and then Chris and I can go through them quickly. The first one is, can you share your career path with the students? How did you pick your college major? And how did you get into your role today? I can quickly answer that and then hand it over to Chris so he can respond. So I'm currently in a marketing and strategy role at my company, but I was in engineering for a long time. I started as a technician, actually at Integer about 18 years ago. So that was very hands-on, building and testing product. Moved into engineering roles, into R&D management roles, and I oversaw our R&D team for about 10 years or so. And then eventually got the opportunity to transition to a marketing and strategy role because I have a business background as well. So I have undergraduate degrees in business and mechanical engineering, and then graduate degrees in business and engineering as well. So I always knew I'd probably end up in more of a business role, even though I started in engineering. And I guess that's the question also asked about my major, and that's really why I selected those majors, both for undergrad and graduate school, because I always had an interest in both the business side as well as the technical side. So that's my answer to that question. Maybe Chris, you could answer.
Yeah, sure. And I've got a similar story. I grew up on a farm, and so we always had equipment. We had tractors. We had all kinds of things. And so I grew up either breaking or fixing mechanical devices. And so that's what spurred my interest in mechanical engineering. I chose to pursue that as an undergraduate path. And I was one of the few engineering students who had interest in business as well. So I took econ classes, I took accounting, and then I also read the Wall Street Journal to keep myself up to date on business things. And then when I started my career as an engineer, it was just natural that I morphed into more of the business functions. And so over time, I can't count the number of jobs I've had in my career, but they've all been technical operations or some type of business that then combined the technical capabilities that I gained as an engineer. So I've always worked for companies that built some type of product, typically in industrial products. And so I've just really enjoyed that. That's why I made the comment that engineering gives a great foundation for anything you want to do as a career in life. So I encourage each of you to continue pursuing that.
Okay, thanks, Chris. Another question here is, what classes inspired you to get into STEAM careers? Again, I can answer quickly, and I think, Chris kind of alluded to this. A lot of it had to do with coursework, so when I was in high school, definitely gravitated towards math and science, solving problems, understanding, why things work and how things work. So that was a part of it, but, Chris alluded to this. It also had to do with my experiences outside of work. I mean, I think you really have to understand where your passion lies. Similarly, I had summer jobs all through high school where I was installing irrigation systems, doing plumbing, doing woodworking, things with my hands, solving problems, building things. And I think it was really that passion along with the coursework that led me towards an education in STEAM. So it's more about what really do you enjoy, and what could that mean for a long-term career?
Yeah, and I didn't talk about coursework very much, but certainly, growing up the way I did, I loved machines. But coursework in high school that really got me involved and helped solidify my decision on engineering were things like physics, AP biology, a lot of my math courses that I really liked. I loved math courses. And so I knew that combination of math and science would serve me well in an engineering curriculum. And so it all was pretty natural. I went to some summer camps. So for any of you that can go to summer camps, whether they be in person or virtual, please do that, because you get exposed to so many neat things, and it helps you decide what you like and what you don't like. And as Andrew said, you really get a chance to find your passion and pursue that passion.
Yeah, thanks, Chris. And there's 4 minutes here, but there's one more question we could answer. So it says, share your personal experience that you had with mentoring that helped you in your college or career. And I'll just say that I really have never been a part of any formal mentoring program, even though some companies and colleges do have formal mentoring programs. So I do, urge everyone, if there is a formal program through your engineering department in college, when you do attend college or even in high school, to take advantage of those. And also, when you join a company. But I would say that you can get mentoring in any way that you possibly can, as long as you're motivated to do so. I mean, I've had a lot of people throughout my career and in college, professors as well as coworkers, bosses, et cetera, that people are genuinely, interested in STEAM, in these careers, in advancing, people's knowledge and careers. So it's just a matter of, having the motivation, the interest, to challenge yourself, to reach out to people. And that's, really at any level, in any setting. There's always somebody that's willing to share knowledge with you and help you along the way. So that'd be my answer to that question. Chris?
And, just like Andrew said, I've never had a formal mentoring program with any company I've been in, but throughout my life, and I go back to being a child, I've always had people, whether they were, close to my age, a little bit older, or even adults, who have always taken an interest. They saw that I had a passion for things, and they wanted to help me. And that's what it's all about. And so when whether you're in high school or start your career, there are always going to be people who form your informal network, and they will see you, they see what you do, and they will take an interest. And when people take an interest, certainly give back to them. Don't make it a one-way relationship. You give as much as you receive, and then you'll find yourself being a mentor to others. And it doesn't end. I've been working 25 plus years, and I've got mentors still that I'm adding to my list of informal mentors as I get older in my career. So keep developing those networks.
Okay, I think that's all the questions we have. So Chris, if you want to wrap it up.
Okay. And again, that's it for today, students. Feel free to send any of your remaining questions to the email address that's on the screen now. And thank you for the participation, and we look forward to seeing you again tomorrow at 1:30. It's been a joy. Thank you very much.